Welcome to a deep dive into concurrent execution, the absolute engine room of modern, scalable software.
It really is.
If you've ever run a high-performance application or, wondered how a web server juggles thousands of users at once without just seizing up, you're looking at the magic
Right.
and the madness of multi-threading.
It's truly a double-edged sword. I mean, multi-threading lets us maximize how we use our resources, which is just essential for performance.
But it's so complex.
Oh, it introduces deep complexity.
Mm.
So our mission today is to give you a shortcut, a crystal clear understanding of the core definitions, the distinctions that trip up even, seasoned developers.
Things like start versus run.
Exactly. Or sleep versus wait.
And then the critical safety nets that, well, keep the whole thing from crashing.
We've got a stack of great sources here, and we're going to be really systematic about this. We're moving from the smallest unit of execution, building up the controls for thread safety, and then finally tackling those famous or maybe infamous concurrency pitfalls.
The ones every developer has to learn to spot and fix. We are jumping right into the nuts and bolts of concurrent Java development.
Let's do it.
Okay, so let's unpack this with the foundational elements first. We hear the terms process and thread all the time. But for concurrent Java, the focus really has to be on the thread. What's its fundamental definition here?
Well, a thread is the fundamental unit of execution. You should think of it as the smallest, lightest instruction set that the CPU can actually run.
So I sometimes hear it called a lightweight subprocess.
Exactly, a lightweight subprocess. But the most important thing to grasp is that Java supports the concurrent execution of multiple threads, which means to the user, they look like they're running at the same time.
And that gets us to the crucial separation, right? Process versus thread.
Right.
So if I launch my web browser, that's a process. But if that browser opens a bunch of tabs and runs its garbage collector in the background, those are threads. What's the technical difference?
It all, and I mean all, comes down to memory. A process is an independent executing program. And its defining characteristic is that it has its own completely isolated memory space.
So if one process crashes, it doesn't take down my whole computer?
Generally, no. It's like having separate houses.
Yeah.
Each one is self-contained.
Separate resource pool.
Exactly. A thread, on the other hand, is a subset of a process. All threads inside a single process share the exact same memory space, the same resources.
And that's where the power comes from, but also the danger.
That's it, exactly. Threads can communicate incredibly fast because they're looking at the same variables. But that shared memory, it's the root of almost every single concurrency problem we're going to talk about today.
It's like your shared apartment analogy. Great for collaboration.
But a high chance of conflict.
Okay, that makes the need for synchronization so much clearer. So if we accept this shared risk for the speed, how do we actually create these threads in Java? What are the two main ways?
So we have two classic patterns. Both involve defining the actual task the thread will run. The first one is pretty simple. You extend the built-in thread class.
And you just override the run method with your code.
Yep, with your business logic.
And what's the second, more favorite approach?
The second is implementing the runnable interface. You still implement a run method, but then you pass that runnable object into a new thread instance.
Okay, so from an object-oriented design view, why is implementing Runnable usually the better way to go? Extending thread seems, a bit more direct.
That's a key design distinction. So Java doesn't support multiple inheritance of classes, right?
Right, you only get one extends.
Exactly. If you extend the thread class, you've used up your one inheritance slot. You can't inherit from any other class.
Ah, I see.
But by implementing Runnable, your class can still extend another base class. It gives you way more flexibility and, well, it's just better design. You separate what runs the Runnable from how it runs the thread.
That makes perfect sense. Okay, let's hit the first major aha moment. The one every developer, myself included, has tripped over. The difference between calling start and calling run. Why is this so critical?
It is absolutely fundamental. If you create a thread object and then you just call its run method, you've achieved nothing concurrent anyway.
Right.
Calling run just behaves like any other normal method call.
Yeah.
It runs sequentially on the exact same thread that called it.
So if my main application thread calls run, my whole app just pauses and executes that code before it does anything else. Zero parallelism.
Precisely. The magic is all in the start method. When you call start, you're actually telling the Java virtual machine to go talk to the operating system.
Ah.
The JVM creates a brand new thread of execution, gives it resources, and then Internally and on its own time, it calls the run method inside that new parallel thread.
So skipping start means you completely fail to use the CPU for real concurrent work. It's the launch sequence, not just hitting play.
It is. It's the difference between asking your partner to take out the trash, which is a sequential task, and, I don't know, cloning your partner to take out the trash while you do the dishes.
That's true concurrency. I like that.
A bit of a stretch.
Yeah.
Did you get it?
Moving on from creation, every thread has this structured journey from being born to, well, dying. Can you give us a quick tour of the 5 stages of the thread lifecycle?
Of course. We start with new. This is just when the thread object has been created, but start hasn't been called yet.
It's on the launchpad.
Exactly. Then you call start, and it enters the runnable state. Now, this is important. It means the thread is eligible to run, but it's sitting in a queue waiting for the CPU scheduler to give it some time.
And once it gets that coveted CPU time,
It moves into running.
yeah.
It's actively executing the code inside its run method.
Okay.
Then we have the state where things get interesting. Waiting or blocked. The thread is still alive, but it's temporarily inactive. Maybe it's waiting for an I/O operation or for a lock to be released.
And finally,
Finally, when the run method finishes or an exception kills it, it enters the terminated state. It's done.
that brings us right to the control mechanisms. We mentioned sleep and wait earlier. On the surface, they both seem to pause a thread, but their functional difference is, well, it's huge, isn't it?
Yeah.
Especially with synchronized code.
Oh, this is one of the most critical points.
Yeah.
Sleep is simple. It just pauses the currently running thread for a specific amount of time.
And it holds on to all its resources.
It does. It doesn't relinquish any locks it might be holding. Once the timer's up, it just moves back to the runnable state, ready to go.
A simple nap, but wait is tied to a much bigger idea.
Wait is fundamentally a synchronization tool. It has to be called inside a synchronized block or method. And here's the crucial difference. When a thread calls wait, it releases the lock it's holding on that object.
Gives up the lock.
It gives it up. And then it just waits until another thread calls notify or notify all on that same object.
Okay, so if I'm holding a lock on a shared resource and I call sleep, I'm basically hogging that resource while I nap.
You are.
But if I call wait, I'm politely handing the key over so someone else can use it while I wait for a signal.
That is a perfect way to put it. That lock release is the difference between writing efficient, cooperative code and just creating bottlenecks. You use wait for cooperation, you use sleep for a simple delay.
We should also quickly touch on a special type of thread that can sometimes fly under the radar, the daemon thread. What's its key characteristic?
Daemon threads are basically utility threads. They run in the background providing services. The most famous example is Java's own garbage collector.
Right.
But their crucial defining feature is that they do not prevent the Java virtual machine from exiting.
What does that mean in practice?
It means if the only threads left running in your application are daemon threads, the JVM just says, okay, all user work is done, and it shuts down.
So if my application finishes, but I accidentally left a regular non-daemon thread running, my whole program just hangs.
It will hang until that thread terminates. Daemon threads are like the cleanup crew that doesn't need to be told when to go home.
A perfect analogy. They're disposable background services.
All right, let's pivot back to that big problem we talked about at the start, shared memory.
Right, this shared apartment.
Because threads share the same heap, variables are vulnerable. If thread A reads a variable, and then thread B changes it before thread A can write back its result, disaster. You get corrupted data. This is why we need synchronization.
We've all seen that random bug, the one that only happens once in 1,000 runs. That's usually a race condition, isn't it?
Almost always. It's two threads racing to modify the same bank account balance or inventory count, and the final result just depends on whichever thread gets there last.
So how does synchronization fix this?
Synchronization is the mechanism that ensures only one thread can access a shared resource or a critical section of code at a time. It uses what are called intrinsic locks or monitors to enforce this mutual exclusion.
Now, when we're implementing this, developers can choose between synchronizing a whole method or just a synchronized block inside a method. This is where performance really matters, right?
It's all about scalability. A synchronized method locks the entire object that the method belongs to.
The whole thing.
The whole thing. Even if your method have 100 lines of code and only 5 of them actually touch the shared variable, all 100 lines are executed while holding that lock. Every other thread needing any synchronized method on that object is just blocked.
That sounds like a massive performance bottleneck.
It can be. And that's why synchronized blocks are the tool for optimization. You can define a small block of code, just the critical section, and you lock on a specific object.
So you're locking a much smaller piece of the code for a shorter amount of time.
Exactly. It lets other threads use non-synchronized methods or even other synchronized blocks on different locks at the same time.
So if my method takes, say, 50 milliseconds to run, but only 5 of those are spent updating shared data, I can use a synchronized block on just that 5-millisecond part.
And you've just made your object available for the other 45 milliseconds. That granularity is the secret to high performance. You want to minimize the critical section to minimize waiting.
Now, what if we want to avoid locking entirely for a certain variable? We want thread safety without the wait. That brings us to thread local.
Thread local is a really elegant idea for isolated data. It lets you create thread-specific variables.
What does that mean?
It means the system makes sure that each thread gets its own private copy of that variable. Since the data is never actually shared, you completely eliminate the need for synchronization for that one variable.
But wait, doesn't relying on thread local kind of defeat the purpose of using threads? I thought the whole point was to share data fast.
That's a great question. It's a key trade-off. Yes, you lose the efficiency of shared memory, but you gain performance in other ways.
Yeah.
Think about temporary state, like a user ID or a transaction context.
Okay.
It's much faster to give every thread its own copy of the user ID than to force all threads to wait in line just to read it from a synchronized location. So you use it for isolation, not for coordination.
Even with all these controls, concurrent systems are they're breeding grounds for failure. So developers have to be able to spot the most dangerous failure modes. Let's run through the 4 big ones, starting with the classic, deadlock.
Deadlock is the mutual waiting game. It happens when 2 or more threads get into an eternal stalemate because each one is waiting for a resource that the other one is holding.
Can you give an example?
Sure. Imagine thread A needs lock B to continue, but lock B is held by thread B.
Okay.
And thread B is waiting for lock A, which is held by thread A. They're both stuck forever.
It's that traffic gridlock in a narrow alley. Neither car will back up.
Perfect analogy. Then you have starvation. This is less dramatic, but just as bad. Starvation is where low-priority threads just never get any CPU time because higher priority threads are always monopolizing the system.
So they're not blocked, they're just constantly ignored.
Exactly. The scheduler just keeps passing them over.
And we already talked about the race condition, which is the whole reason we need synchronization in the first place.
Right. That's the fundamental problem when you don't have enough synchronization. Your output becomes unpredictable because it depends on the random ordering of execution.
And finally, the most, frustrating one, live lock.
Live lock is the polite, feudal dance. Unlike in a deadlock, the threads are not blocked. They're actively changing states.
So they're doing something.
They're busy, but they're not making progress. They're usually trying to resolve the conflict. Maybe they release a lock, see the other thread has a lock they need, release their new lock, and just repeat that cycle over and over. They burn CPU cycles, but do no actual work.
That sounds like a developer's nightmare. The system looks like it's running, but nothing's getting done.
Precisely. Busy, but not productive.
Fortunately, modern Java has made managing threads a lot easier than just manually creating and tracking every single thread object. We're talking about the Executor framework.
Yes.
What problem does this framework solve for us?
The Executor framework is really the modern solution. Manually creating and destroying threads is an incredibly expensive operation for the OS. So the framework introduces thread pools.
A set of reusable threads.
A set of reusable worker threads, exactly. Instead of creating a new thread for every single task, you just submit the task to the pool, and ready worker thread picks it up and runs it. It dramatically reduces overhead.
It's like having a permanent staff waiting for orders instead of hiring a new temp worker for every delivery.
Absolutely. It manages the life cycle and the resource limits for you.
And within that modern approach, we have tools that go beyond the basic, fire and forget style of Runnable. I'm thinking of Callable and Future.
Right. Callable is an evolution of Runnable. It does the same thing, defines the logic to be executed, but with 2 critical additions.
Okay, what are they?
First, unlike run, a callable is designed to return a result. And second, it can throw checked exceptions, which makes error handling much, much cleaner.
And Future is how you get that result back.
Exactly. When you submit a callable to the executor, you get a future object back instantly.
So it's like a placeholder.
It is. It's a placeholder for the result. You can use the future to check if the job is done. You can wait for the result to complete, or you can even cancel the task. It decouples submitting the work from getting the answer.
It's basically the receipt that guarantees you an answer is coming.
That's a great way to think about it.
We've covered a massive amount of technical ground here, from the, molecular level of a thread up to these complex frameworks. If you're starting out or trying to optimize a concurrent app, what are the 3 big takeaways?
Okay, first, you have to solidify your understanding of memory scope. Processes isolate memory, threads share it. That shared memory is the source of all your power and all your pain.
And second?
Second, never, ever confuse start with run. If you don't call start, you aren't doing concurrent execution, period.
Right.
And third, be strategic about synchronization. Don't lock more than you absolutely need to.
And that strategic application is everything. You have to be able to recognize the signs of those failure modes. If your app stalls, is it a deadlock or a live lock?
If your data is getting corrupted, you've got a race condition.
Learning to debug those 4 issues is just mandatory.
It is. And to tie back to our discussion on synchronized blocks, maybe here's a final thought. When performance really matters, locking an entire resource with a synchronized method is rarely the best approach.
Right.
Knowing that a synchronized block can lock just a tiny sliver of code is the ultimate tool for scaling your application. For your own explorations after this, maybe look into how Java's more advanced locking tools, like a reentrant lock, expand on that idea of granular control. Think about why managing access to a single variable is often more important than locking the entire object it lives inside.